right, 12.1 goodness of fit test. All right, so again, we have our characteristics of our chi-square distribution. We've talked about those before. None of that has changed. We're dealing with this. So a goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. Okay. So we're going to be looking at expected counts. An expected count is what we expect to get out based on our probabilities. Okay. And so that's what all this is. We would just multiply our total number, times our probability for each one of those in order to get our expected count there on those. Okay. All right. So here, just finding our expected counts, we have income for households, and we have the percentage for each one of those. Okay. That should be in that income. All right. So if we wanted to find what is the probability of each one of those, we just move the decimal over. So the very first one there is 9.9%. So we move that over and we get 0.099. Okay, so that's what all of these things are here. Now, to find the actual expected counts, there were 1,500 total people in our survey, in our sample, and so we multiply by each one of those probabilities. So for under 1,500, we would do 15,000, 1,500 times 0.099. Now again, the 1,500 comes from the number in our survey. And if we go back and look at our problem, we can see that right over here for our pieces, okay? It's not from the 15,000, it's from the 1,500 households in our problem. Okay, and so we would multiply each one of those 1,500 times every one of those percents we have there, and the result would be how many homes that we expect to be making that much money, okay, what their income should be. Okay, so every one of those, all they're doing, multiplying 1,500 times that percent. Okay. All right, now, what about our test statistic here? So we're going to have our chi-squared. Now, again, a lot of this we're going to do in the calculator, so it's not going to be that big of a deal for our pieces. But we are going to have to remember that we have degrees of freedom because we're talking about chi-squared here. And so we're going to keep that in mind. It's always -1 for whatever our n is. Okay. All right, now, goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population, okay, on those. All right, so we need to first determine our hypothesis, null and alternative, for those. What is the level of significance? And then calculate our expected counts with those, and then verify the requirements here that all expected counts are greater than or equal to 1, and no more than 20% of the counts are less than 5. Okay. All right, so then we would compute our test statistic and then compare that against our critical values for our chi-squared. Okay. All right, and then we can also do our p-value as well with these pieces, okay? And we'll use the calculator on all of those. All right. All right, so again, let's go back to our 1,500 households. Now this time they actually went and looked at some data, and so they observed a certain number of homes out of the 1,500 and what they actually did compared to what we expected them to be, okay? And so from moving on from here, in order to find our pieces or goodness of fit, what is our test statistic value and our p-value, we need to let that calculator work for us, okay? And so our observed accounts, observed will always go into L1, expected will always go into L2 when we're looking at those pieces. Now, based on the calculator you have, it's going to determine how much more work that we need from here, okay? So I'm going to put up a little page here on the side that's going to tell us based on what we have here, okay, for those. So in 12.1, that's where we're at here. So if you have a TI-83, we're actually going to have to do quite a bit of work because the TI-83 does not have the program that the TI-84 has, okay? And so we want to look at it. Now, if you have a TI-84, you should have that you have under stat and test, if we go down, there should be a chi-squared GOF for goodness of fit test, okay? If you don't have this, then you're going to have to do what we do up at the top, okay? Now, for everybody, L1 is observed, L2 is expected, okay? So let's go ahead and go through those pieces here. Now, I'm going to do the 83 version first, and then I'll go to the 84 version on those pieces and show you how we work through them, okay? All right. So here we are. I'll go line by line. So we put in L1 and L2. So we go to stat, we go 1, and so we go in L1 and L2. Now I already have everything here in L1 and L2. And so I need to go to my next piece. So my next piece says, in L3, we need to do this formula. So anytime we need to do a formula, we need to arrow up and highlight the L3s. Now that we're in L3, we're doing everything here. We can type in what I have up there, okay? And so we open our parentheses. We're going to do our observed L1, so second 1 for L1, minus second 2 for L2. Close parentheses, square it, and then divide by L2. Okay, so it's going to be that formula every time when you're doing these problems. Okay, and then we press enter. And that gives us a bunch of values when we're looking at these pieces. Okay, we have a lot of different things going on there. All right, now let's move down here a little bit. So now we want to quit so we don't mess anything up. So second mode is our quit button there. And so now we're going to go into second stat, and we're going to go over to math. Okay, so we're going to go over to math, and then we're going to go down to sum. We want to add a bunch of things together. So we're going to add those together by hitting sum, and we want to do L3. So second 3 for L3. So we want to add up everything in our L3 list that we just created. Okay? And then we press enter. Now that number is our test statistic. Okay? And so when we're looking back here at our pieces, if we go through, they do all of this work here, and we'll see that, bam, their test statistic is 20.693, which is exactly what we have right here. Okay, that is our test statistic, and that's how we're going to do that on the 83 model for these. Okay. Now, what about our p-value? Now, our p-value is looking at things a little different. So, again, we want to do some things here. Now, my calculator is going to ask some other questions, and so we're going to ignore some of that because yours doesn't do that on the 83s. So, we do second vars, and we need to do our chi-squared CDF. So number 8 here for me, chi-squared CDF, and press enter. Now I'm going to ignore all this stuff. I'm going to just press paste and go back and delete everything. On the 83s, that's not going to happen for you, so you're not going to have to worry about that, okay? We're just going to clear it out. Yours should pop up and look like mine now for those pieces. Now we need that 20.693, but we're just going to cheat. We're going to say second negative. That gives me my previous answer. Say ANS, that's my previous answer. So I want that 20.693 right there, comma. Now, because we're looking at a right-tailed here, we're going to do 1E, so second comma, 99, and then comma, our degrees of freedom. Now, we go back and look there, our degrees of freedom for L3, there were 9 things in there. So 9 minus 1 is 8. Okay? For those. And we press enter, and we get 0.008. And that is our p-value. Okay? For those. All right, so you can see here they also got their degrees of freedom on those. Now, when we're looking at what are we doing with these numbers, do we reject or do not reject? Well, we need to go back and look at our critical values. We had a significance of 0.5, so we need to do our chi-squared of 0.05 at 8 degrees of freedom. And so that's 15.507. Well, we are greater than that, so we would reject the null hypothesis for our test statistic. Okay? Now, what about the p-value? They go through, again, they do all that same stuff, and they get this value, just like we did, 0.008 for their p-value. Well, that is less than 0.05, and so therefore we would reject the null hypothesis. Okay. All right, now let's try another one just so we can go through those pieces again. Okay. So here we have an obstetrician that want to look at the proportion of children born on each day of the week. And we know that's the same. We have 500 births. What is the frequency compared to what is expected? Okay. So our frequency, that's our observed, is already listed there. So that's what's going to go into L1. Okay. Now, what about into L2? Well, every day has the same percentage. It's 1 out of 7 because it's just, that's how many days there are in a week. Okay. Nothing shows different than that. They all have an equal amount of being chosen on those. Okay. And so if we take our 500, multiply by 1 over 7, every day has a probability of 70, has an expected value of 71.4, okay, for those. And so we would then go in. Now, they're doing the full by hand. We're going to use that calculator to do those pieces for them, okay? So I'm going to clear that off. And I'm going to go back into stat. Here, I'm going to do number 1. And I'm going to press clear, enter, and then clear, enter here for those, okay? So let me go back to my chart here. Sorry. A little ahead of myself. All right, so our observed was 46, 76, 83, 81, 81, 80, and 53, okay? And then we expected there, we said we did our multiplication, and all of these should be expected at 71.4. Did that one wrong, 71.4. Right. They all have the same values, okay? Now, our L3 is still going to be that same formula that we talked about up here. And so L1 minus L2 squared divided by L2. Okay, so we get those values. All right, so now we need to quit for those. We're going to go into second stat, over to math, and do the sum of L3. So we should get 19.57, okay? Which is close to what they have, right? Again, there's going to be some rounding errors on those pieces. Now, if we want to do our p-value, we go into second vars, go down to our chi-squared CDF. Again, I'm just going to paste that in and delete all of that. So I want to do second negative for my previous answer. 1 E99, comma, and our degrees of freedom. Well, there's 1, 2, 3, 4, 5, 6, 7. So that means there's a degrees of freedom of 6. We look at that, 7 days of the week there. And we're going to get a p-value of 0.03. Okay. All right, so when we start looking at our degrees of freedom and our critical value of 0.01 there, we see that we are again to the right, so we would reject the null hypothesis. All right, and even using the p-value, that is less than the 0.01 that we wanted. 0.003 is less than 0.01 with those, okay? All right, now what about if you have an 84? I forgot to do this a minute ago. If you have an 84 already, then you will have to do a lot less. So let's just kind of go through this problem that we had right here. Let me go back up so we can see and compare some values with those. All right, so let's clear that off. So we already have L1 and L2 with our observed and expected. So we're just going to do here our stat. I'll go over to test. We're going to go way down to our x squared, our chi squared g of f test. So we had 1. Now this time we said that our degrees of freedom was 6 because there are 7 days in the week. 7 minus 1 is 6. And we calculate. And you can see there as well that I got the same values, 19.57 and 0.003 for my p-values on those. Okay, so the 84s do make it a little bit easier to get those pieces. Okay. All right, and so again, we would reject the null hypothesis. All right, so those are the things that we're going to need here in 12.1.